Welcome back. Today we're going to define systems of equations and we're going to solve those systems of equation by graphing. So by definition, a system of equations is two or more linear equations. So here are three examples of systems of linear equations. All of these have just two linear equations. We could have three or four, but we're going to stick with two at this point. So 3x minus 3y equals 0 and x equals 2y, a system of equations. And here in the green, another system of equations, another system of equations. We've got three different samples of systems of equations. Now, the solution to a system of equations is any ordered pair that satisfies both, in our situation it's both, the equations in the system. So as you can see, our equations have an x and a y, so we need an ordered pair x and y that satisfies both the top equation and the bottom equation. It's got to work for both. If it doesn't work for both, then it does not satisfy the system. And here we have three different visual representations of solutions to a system of equations. So the black lines here indicate the graphs that we would get by graphing our system. So on the far left, we have two lines that intersect at one particular point. So that point of intersection would be the solution, that ordered pair, x and y, whatever that may be. Okay, it looks like here it's 2, the x seems to be 2, and the y, I don't know, seems to be about approximately -1/2. So that would be the solution to that system. Okay, and those two equations in that system would be considered independent. They are independent equations, and that system as a whole would be called a consistent system. Consistent system is a system in which there's at least one solution, and our one solution here seems to be around 2, -1/2. Another example is two parallel lines. Okay, now again, we have two independent equations. As you know, two parallel lines are lines that have the same slope but different y-intercepts. Okay, so again, we have independent equations, but this is now an inconsistent system because there are no solutions to that system of equations. Parallel lines, as you know, will never meet, so there is going to be no x and y that would satisfy the equation for the bottom line and the top line. And here on the far right, our final representation, we've got two lines. It looks like we've got a red line and a black line, and they are right on top of each other. So that would be the same equation for that line. So we'll have at least one solution. In fact, we'll have an infinite number of solutions. Any ordered pair on this line will be a solution to the system. Okay, and those are dependent equations because essentially it is the exact same equation. Might have a different format, but it still has the same slope, has the same y-intercept. Those two lines do, so they will be dependent equations, and that is a consistent system. Let's take a look at our first sample. Let's take a look at our first sample problem here. Let's solve this particular system by graphing. I'm going to take the first equation and let's go ahead and put that equation into slope-intercept form. So that's going to be y equals, I'll add the 3x to both sides, and that'll become y equals 3x minus 10. So my y-intercept is down at -10, so I'm going to count by 2's. I'll -2, -4, -6, -8, -10, and I'll rise 3, okay, and run 1, so that must mean I'll rise 2, 4, 6, and run 2. Okay, and I'll rise 2, 4, 6, and I'll run 2. Okay, and have a general idea here of where my line is. There's an advantage of having a straight edge and being real careful about your graphing and using graph paper with the graphing method. The second line, I'm going to just graph using the x and y intercepts. So if I put 0 in for x and solve for y, well, y is going to have to be -6, and I'm going to go by 2. That'll be that particular point right there, and I'm going to put 0 in for y and solve for x, and that is going to be 6, so that'll be that point right there. So I will go ahead and graph that line. I know my slope of this particular line is 1, so I'm going to have a point here, and I'll have a point here, and this is the graph of x minus y equals 6, and there is my intersection at 2, -4. So the solution to that system is the intersection of those two graphs at 2, -4, and that should work in both equations. And just eyeballing in the second equation, 2 minus a -4 equals 6. That checks out, and when x is 2, I get -3 times 2 minus 4 equals -10, and sure enough, -6 minus 4 does equal -10, so that checks out. So yes, that ordered pair checks out. It does satisfy those systems both graphically and algebraically, and our system, since the lines intersect, we've got a consistent system with independent equations. So our system is consistent and independent. Let's work on the second sample problem. We'll solve this particular system by graphing. Let's take a look at these a little differently. 3x minus y equals 6. Well, the slope of that first problem, without finding the x and y intercepts, it's in standard form, so we can do this opposite of a over b, which would be -3 over -1. So our slope of that first one is 3. Okay, and the y-intercept, if we put 0 in for x and solve for y, the y-intercept is -6. So 1, 2, 3, 4, 5, 6, and it's got a slope of 3, so rise 3, run 1, rise 3, run 1, and there's the graph of our line. Second equation, we will go ahead and divide by 2. It's really close to slope-intercept form. We get y equals 3x plus 0. So the y-intercept is there. Wait a minute. This one has a slope of 3. Both lines have a slope of 3. They have different y-intercepts. These two lines are parallel. These two lines are not going to meet. They have the same slope. So we are done graphing. There is no solution for this. There's no ordered pair that'll satisfy both the green line and the blue line. Okay? These equations, since the lines are parallel, going back to what we saw before, here we have parallel lines. They're independent equations, but an inconsistent system. So, they're independent equations and inconsistent. Moving on to sample problem 3. Now we're not going to graph. We're going to do something a little different here. Without graphing, determine the number of solutions to the system. Well, let's take the lessons learned from the previous sample problem. Hey, if we have parallel lines, there's going to be no solution. If we have intersecting lines, we're going to have one solution. If we have the same line, we will have an infinite number of solutions. So let's just take a look at this. These are both in standard form. So the slope of this first particular problem is the opposite of A over B. So it's negative 1 over 3. The second one has a slope of opposite of A over B, negative 4 over negative 1 equals 4. Well, we have different slopes, so we know that we have intersecting lines. And therefore, we will have one solution to our system, one ordered pair. X and Y will work and satisfy both of those equations. Not asking you to find out what it is, but just that we have one. So that wraps up the graphing method. Okay, we have seen we have a variety of solutions. We can have intersecting lines, parallel lines, or the same line. We know that the solution to the system is any and all ordered pairs that satisfy all the equations in the system, and some examples of systems of equations. So that wraps up graphing method. We will see you in class.